Hey friends, welcome to 1 Minute Math. Today we're going to be talking about extrema, finding the maxes and mins of a function, maxima and minima. This would be an AP calculus or like a calculus 1 kind of concept. This is one of the first and most classic applications of using the derivative of a function. So first, let's talk about extrema. Let's talk about maxes and mins. If I asked you where are the maxes and mins on this graph, or the maxes and mins of this function f of x, I hope you have kind of an intuitive idea of what that means. Like a maximum value ought to be a high point. And I do see, like, it looks like a y value of 7, this point 6 comma 7. It looks like that is the highest point achieved anywhere on the domain of this function. So it makes sense to call that a max. And when I say that, I mean 7. I'm going to say the max is 7. Okay, the point, it's okay to identify a point where a maximum occurs, but when we're talking about a maximum or a minimum of a function, what we mean are the highest and lowest values of that function. Those would be the y values or the f of x values. So I'm going to be real specific about that. If you're in my class and I ask you what's the maximum of this function and you say the maximum is the point 6 comma 7, I don't give you credit for that because that's not 6 comma 7 is not a value. That's not a maximum value. Anyway, so there's a maximum, but what about this other point over here? There's this point 2, 4.5 that sure looks like if I were just zoomed in on that little area and I didn't see the whole picture of the entire function, it looks like a maximum value is occurring there. And we're not wrong to point that out. So we're going to need to qualify these a little bit. I'm going to call this thing over at the 0.67, this maximum value of 7, I'm going to call that the absolute max. It is the absolute highest value on the entire domain. And then the value of 4.5, happening at the point 2 comma 4.5, that is a maximum, but it's not the overall maximum of the entire function. So we're going to call it the relative max. And other words that you might use for this would be, we could also call this guy the global max. 7 is a global max, and then 4.5 is a local max. Down here at the point 4 comma 2, the minimum value achieved by this function anywhere is the value of 2. So we're going to call this the absolute min or the global min. Absolute minimum equals 2. It happens at the point 4, 2. The absolute min is 2. And then you're thinking to yourself, okay, so this guy over here, he's going to get a name too. And they're kind of like two different schools of thought here. I am not going to identify 3 as a relative minimum. And we'll talk about why in a minute. Like 5 out of 10 math teachers, if you're talking to your teacher and they say, oh yeah, always classify the endpoints of the domain as either absolute or relative extrema, that's fine. Like, do whatever your teacher asks you to do in that case. And most of the time, we ask questions in a way that's not going to lead you to say something controversial. And again, we'll get back to how these concepts are presented and how they're asked here in a minute. So just to clarify, global absolute max is the highest value attained by the function on its whole domain. And the whole thing that you're given, the highest value overall is the global max. Then that makes a local or relative max the highest value in a small area. And technically, the word we use for this is neighborhood, which I love. I love that we use the word neighborhood to describe an open set around the point in question. It's like where the point lives in its neighborhood. So not every function has any maxes or mins, relative, absolute, anything. So here's the function y equals 1/3 x cubed. It's got no maxes or mins at all. If I restrict the domain, however, now I've got some. Now there's an absolute maximum value of this curve at 8/3 and an absolute min of negative 8/3 just by restricting the domain. Interesting, interesting. So not every function has maxes and mins. And the other takeaway from this picture is that oftentimes what we call the max or the min value or what we classify as an absolute max as opposed to relative max, etc., depends on the domain we're looking at. This is really important when it comes to word problems. If I take the same function in a very similar domain, but now I'm excluding the endpoints, I'm not including x values of 2 and negative 2 in my domain considerations, now there are again no extrema. An extremum, by the way, it's a fun vocabulary lesson. Extremum means a maximum or a minimum. In the same way that you might use the word sibling to mean either sister or brother, or spouse to mean either husband or wife, extremum, maximum or minimum. And so a plural, extrema, if I have more than one extreme value that I'm talking about, they are extrema, which means if I have more than one max point, I'm going to call them maxima and minima. Those are the technical plurals for those words. All right, here's another one. Here's another picture of a function. And you'll just take a second. We'll check and see if you get this. Got an absolute maximum, which is 1, 2, 3, 4, and an absolute min, which is 0. Right? I give this question on quizzes, and very often I have students who tell me the absolute maximum is 0 and the absolute minimum is 4, because they're looking at the x values. If you think about what you're saying there, it'll make total nonsense, right? An absolute max can't be less than an absolute min. The absolute max has to be greater. Please make sure you're using the y values. That's important. Here we got another guy. I've got an absolute max up here. That looks like a y value of 3. I do not have an absolute minimum value. I've got a relative max happening here at the point x equals 0. That's a relative maximum value of 1. I've got a relative minimum happening here at a y value of -1 and x value of 2. And this guy, he's an endpoint that's not an absolute extremum, so I'm not going to give him a name. And notice how I am not going to just identify this point, this turning point to -1. I'm not going to say that an absolute minimum occurs there just because it's the lowest minimum point on the graph, because it is not the absolute lowest point on the entire domain. There are y values that are less than -1. So I can't call this relative min. I can't say that's just going to be an absolute, because it's not. There are lower values. And there is not a lower value that is attained. There's not a lowest value that's attained, so I'm not going to identify an absolute min. There's no absolute min. And here's another one. Here's a graph where we have no absolute max. We've got a relative max occurring at x equals 2. The relative maximum value is 0. I've got a relative min occurring at about 3.5. That's the value of -1.5, like I said. And then we've got an absolute minimum right here of -2. Okay, hopefully that one made sense to you. Let's jump into, we're going to skip this guy. We're going to jump into another interesting example. We'll make some conclusions about how we can look analytically at these curves, and then we're going to solve some problems analytically without looking at the picture. So if I give you pictures like this, if your teacher gives you a picture, you see a picture on the test, and it says like, identify all of the extrema. I hope that that feels like it's going to be an easy problem to you. You can like visually tell where the highest and lowest points are, and you can classify them. Are they the highest point overall in the entire graph? Or are they just the highest one in a local area? But when it comes to not looking at the picture and having to rely on functions that are presented algebraically or numerically in tables of values or with other information we know about the graph, how do we conclude what the maxes and mins are? And that's coming here in just 2 seconds. I picked this one though, our last graphical question here. I hope we identify that we got a relative max of 5 happening at x equals 0. And x equals 0. And this fun guy here, that's a relative min, which has a value of 3 happening at x equals 1. And this arrow up here tells me that the turning point at x equals 0 will not represent an absolute maximum, because that right branch of the function just goes on for infinity. And obviously this relative min here happening at the point at x equals 1, that's not going to be an absolute min, because I got all these points down here that have lower y values. So there are no absolute extrema on this graph. That's not necessarily the interesting point. What I think the interesting point is it's like literally a point. That turning point right there. We're going to make some conclusions here. And my first questions to you are, what is happening at these relative maxes and mins? What's happening at the local maxes and mins? And if we look back at our curves, now here we have 3 very similar looking points. We got a relative max, and this absolute min, like he's a relative min too. Local things that are local are also global, right? Most of the time. So this absolute min, what I mean is things that are global are also qualify as local most of the time. So this absolute minimum occurring at this point also qualifies as a relative minimum because -2 is the lowest value in a neighborhood. It's the lowest value in the entire function, but it's still the lowest value in the neighborhood. And if we're thinking in a calculus perspective, right? Hopefully you're thinking about the derivative. If the curve I'm looking at here is f, I could say something about f prime. Like f prime here is negative. F prime here is negative. F prime on these branches, let's go orange. F prime on this part is positive because the curve f is increasing. F prime here is positive. And do you notice how these turning points, the relative maxes and mins are occurring at the x values where f prime changes sign? We're tempted to say equals 0, right? Did you expect me to say equals 0? On this picture, that it does. F prime equals 0 here, here, and here. Those are all flat points on the curve. But more importantly, it changes sign. If I go back to these guys, I drew this curve actually kind of poorly because it does actually go totally flat here in the middle just for a moment. If I drew this curve better, it would be completely flat there for a minute in the middle. And if you know anything about derivatives, you could find the derivative of this curve pretty easily. It's x squared. And so therefore we know that the value of the derivative, y prime or f prime of 0, is going to be 0. Is there a max or min happening at x equals 0? There is not. So if maxes and mins, if our relative maxes and mins are going to be happening at these, what we would call turning points, places where the curve turns around. It was going uphill, now it's going downhill. Or it was going downhill, now it's going uphill. F prime doesn't have to equal 0, but it does have to change sign. And this guy, this last one, is our great example of f prime was negative, f prime was positive, f prime changes sign, and it definitely did not equal 0 at x equals 1. F prime is undefined at x equals 1 in this picture. So what can we say about f prime at a local max or min? F prime changes sign. And if f prime changes sign, that means that f prime equals 0 or is undefined. Can we use that fact to identify local maxes and mins? Absolutely. So let's do that problem first. We're going to come back and answer the remaining 2 questions on this slide. But here's a great classic question. Use analytic methods to find all the extreme values, maxes and mins of this function that I've presented. So I just talked about how f prime is kind of the key to these things. So let's go ahead and find f prime. F prime, just using the power rule, it's going to be 3x squared minus 12x plus 9. We can do this all without our calculator. My algebra instincts are yelling, factor me, factor me. Okay, so I'm going to factor this guy. Oops, 4x plus 3. And that gives me 3 times x minus 3 times x minus 1. All right, what are my conclusions here? Well, f prime equals 0 when x equals 1 or 3. Have I found my max and min values? Not quite, but I'm getting there. So now I know that if there's going to be a maximum or minimum value that occurs on this function, it's going to happen at either x equals 1 or x equals 3. There's nowhere else it could happen because these are the only 2 x values where f prime might change sign. So does f prime change sign here? Let's find out. Hopefully this process of evaluating the sign of a function, this should feel familiar to you from a previous math class. If not, I'm basically doing what we call like a nonlinear inequality. I need to figure out if f prime is positive, negative, or 0 on these 3 intervals of the number line. So for example, if x is greater than 3, and I'm going to plug that in here. Let's just find f prime of 5. Okay, that would be 3 times 5 minus 3 times 5 minus 1. I don't need to compute this value. I just need to figure out if it's positive or negative. And I can see that I've got 3 positive numbers that are being multiplied together. That's definitely going to give me a positive number. Just for funsies, let's try the other end. What if I plug in x equals 0? That would give me 3 times negative 3 times negative 1. I've got a positive number times a negative number times a negative number. That's also positive. I could take a good guess and say f prime is probably going to be negative in the middle. I could use my understanding of what f prime looks like. F prime is a quadratic. It has two zeros. It's very likely that f prime is going to be negative between those zeros. In fact, I could probably prove that. But let's be totally thorough here. This is the first one of these that we're doing. I'm going to plug in x equals 2 to my derivative. I'm finding the values at f prime. That would give me 3 times -1 times +1, and indeed that is a negative value. F prime is 0 at those two things. What I can conclude about the behavior of f, without knowing the exact nuances of what f looks like, I mean, I can take a good guess because it's a cubic function, and I've taken pre-calc. I understand what cubic functions are supposed to look like, but I at least know that f is supposed to be increasing and then flat for a moment, and then decreasing, and then flat for a moment, and then increasing again. I am making that conclusion based on the sign of f prime. And just based on that, I can conclude that there is a local min happening at x equals 3 and a local max. Are they global? Maybe. I don't know. I haven't been asked to determine that. A local max happening at x equals 1. All I can conclude from the behavior of f prime is whether there's going to be a maximum, minimum, or neither at any of these points. These are what we call critical points, by the way. A critical point, there we go, point, which is a better word for that would be a critical value. Because we're going to be talking about x values. Critical values are an x value where f prime equals 0 or f prime does not exist. Those are what we call critical points. And critical points are the only points that could potentially be maxes and mins, where maxes and mins could possibly occur. So I found my two critical values. I plugged those numbers, or I found the intervals of the number line that those critical values separate the number line into. I determined the sign of f prime on the entire number line using those as my like break points, and I've made conclusions about what's happening at those points. Have I answered the question? Not quite. I found the x values where the relative max and the relative min occur, but I have not found the actual extreme values. So now I got to go back to f and plug in my numbers and come up with the actual maximum and minimum values. I do not have a calculator handy, but we can do this. Okay, 1 minus 6 is -5 plus 9 is 4 plus 2. F of 1 is 6, and that is a local max. F of 3, okay, this is going to be 27, 27, that's 54. 6 times 9 is 54, so those cancel out, and I get 2. F of 3 is 2, and that is a local min. Fantastic. Ta-da! We used the fact that f prime equals 0 or is undefined at maxes and mins in order to find where our local maxes and mins are. So that if I present a problem like this in class, very frequently somebody raises their hand, but Mrs. Thomas, how do I know that there's not a max or min somewhere else? Well, it's just a cold hard fact that a max or min will not occur anywhere but a critical point. Period. If we're talking about local maxes and mins, they will never occur anywhere that's not a critical point. So if we identify the critical points, we have our candidates for where the maxes and mins could occur. Now, what if I change this function or change this question ever so slightly? The same function, it's going to have the same derivative, it's going to have the same local max and the same local min, but now I have made a closed interval. Okay, let's think about what this curve looked like. Without knowing more about it, just kind of based on what I know about the derivative and kind of my basic pre-calc understanding of how this curve behaves. I knew that there's going to be a relative max happening at 1. There's a relative min that's happening at 3. And this is my basic overall picture of what this function looks like. Now, if I close off the endpoints of this domain and say I really only want to look at the blue portion of this curve, do you see how now I can care about absolute maxes and absolute mins? So let's go back here to this question. What is f prime at an absolute max or min? Well, sometimes it's zero, sometimes it's undefined, and sometimes it could happen at an endpoint. So can I use f prime to identify absolute maxes or mins? Kinda. So critical points are points where local maxes or mins could occur. Absolute maxes or mins could occur at critical points or endpoints. Let's go ahead and see if we can just kind of brute force finish this problem. All right, I already know these facts about the function, or these facts about this problem. I need to get my values over here because I forgot. Okay, 6 and 2. F prime of 1 equals 6, and this represents a relative max, or local max. I know that f of 3 equals 2, and this represents a relative min. And if I'm trying to ask the question of where are the other potential maxes or mins, or are there other potential maxes and mins, looking at the behavior of this function, I've got to check, is f of 0 higher or lower than my other potential absolute min? And is f of 5 higher or lower than my other potential absolute max? Because without knowing more about the function, it could actually look something like this, where 6 and 2 would be my absolute max and my absolute min. Maybe the absolute min is happening at 0, though. I don't know. The only way for me to check is to actually plug 0 and 5 back into my original function and see what values I get. 0 is easy. I get f of 0 equals 2. F of 5, it's going to be 125 minus, what's 6 times 25? 150. Gives me negative 25. Okay, so negative 25 plus 45 is positive 20. 20 plus 2 is 22. Based on these numbers, I can see now that the smallest value that's obtained by this function on its closed interval will be 2, and the highest value that's obtained is 22. Adding the closed interval to this problem changed it a little bit. I no longer just need to find the critical points, but I need to evaluate f at those critical points and the endpoints and figure out which is highest and lowest. Are there two absolute minima? No. The absolute minimum of this function is 2. The absolute minimum value attained by this function on its domain is 2. It occurs twice. It occurs where x equals 0 and x equals 3, but that's not when I ask. When I ask for the extreme values, I'm talking about the y values of the function, and there can be only one absolute minimum point. There can be only one absolute maximum. That the value might be represented a dozen times, but the absolute maximum or absolute minimum is only one number. Sweet. Okay. So pause this and write some stuff down if you would like. If you get the find the extreme values problems, the basic procedure here is you're going to take the derivative, find all the critical points, use some kind of analysis of the derivative to determine if those critical points are going to be maxes or mins. And if you are given a closed interval domain, you need to evaluate the original function f at all critical points and the endpoints to determine your absolute max and min. I'm sure that I have another problem here. And typically the way, well, let's look at a problem before I tell you how they're worded. The closed interval test or the extreme values theorem, this is an important theorem. It says that every continuous function attains an absolute min and an absolute max on its closed interval domain. So if I have any connected function, doesn't matter what it looks like at all, and I restrict the domain somehow, I say I only want to go from this point to this point, that guarantees that the function will have an absolute max and an absolute min. Critical points, any x value at which f prime equals 0, f prime does not exist. And stationary points, if we're just talking about the places where f prime equals 0, we call those stationary points. Part of the description, part of the vocabulary is not essential. Extreme values occur at critical points or endpoints. So in other words, an extreme value of a function will never exist anywhere except a domain endpoint or a place where f prime equals 0 or does not exist. That's a super handy fact. And when you evaluate, when you're asked to find absolute maxes and mins, what we say about that, like finding f at all those values, we call it a candidates test. When you see an absolute max or min problem, this is your strategy. You want to use F prime to identify any candidates for extreme values. So it'd be critical points or endpoints. Then you basically make a table of values of X and F of X, and you classify those extreme values using some kind of additional analysis. You're going to plug the X values back into F to make a table of values to find the absolute max and min, and then you'll use the signs of F prime to classify any relative extrema. Now that we're talking about relative and absolute extrema in this way, do you see why like a local max or min occurs where f prime changes sign? That's not what happens at an endpoint. So that's why I'm in the camp. I told you before, 5 out of 10 math teachers will say, oh, yeah, you can call a domain endpoint a relative max or min. And the other half will be like, no, you really can't. I'm in that, no, you really can't kind of camp. Because if we're going to say a relative max or a local max happens where f prime goes from positive to negative, which is what a relative max is in a neighborhood, it's the highest point, and it's a turning point, then that is not what's happening at an endpoint. And we shouldn't use the local max or local min vocabulary to talk about those. Now, the way the problems are typically presented, if we're talking about local maxes and mins, we'll get back to this problem in a second. If I'm talking about local maxes and mins, the problem typically says something like, here's f of x. Blah, 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 blah. Sometimes it's even presented graphically. Sometimes f prime is presented graphically. Sometimes we're given a table of values. And the question will say, identify all critical points or all critical values. And once you identify the critical values, then this next part of the problem says classify or determine whether a max or min, whether a max, min, or neither occurs at each of those critical points. So that if you understand what a critical point is, you're not going to include the endpoints as critical point unless f prime actually equals 0 there, or is undefined. And then you won't have to decide whether those endpoints are going to be relative maxes or mins because they're not critical points, so they're not even part of this problem at all. So that's how problems are typically worded to make sure that you're not put on the spot to have to like choose whether or not you're supposed to call domain endpoints maxes or mins. All right, one last problem. I'm just going to do one final problem here. And this is an easy one. You know what this function is going to look like. Negative x squared plus 2x plus 4, that's going to be one of these guys. It's an upside down parabola. You have an idea of what's happening, but we're going to use calculus to solve this one anyway. Take f prime, negative 2x plus 2. Okay, find my critical points by setting f prime equal to 0 or finding where it does not exist. This is a linear function. It's not going to have non-existent points anywhere. So I'm just going to set it equal to 0. X equals 1. Fantastic. That's my only critical value. I'm going to plug that into f prime. Well, not 1, but like the two intervals that determine that separates the number line into the real number line. If I plug in a number that's greater than 1, I get a negative value. If I plug in a number less than 1, I get a positive value. So that tells me my function f has this kind of behavior, increasing to decreasing. So I know that there's going to be a local max happening at x equals 1. Knowing what I know about quadratics, there's also going to be an absolute max happening at x equals 1, but I'm not going to jump to conclusions. It wants me to find and classify all extrema on a closed interval, so I must do this table of values that we call the candidates test. My candidates here are the endpoints 0 and 3, and any critical points I found, which is 1 is the only one. I'm going to plug those values back into my original function f, not into f prime. If you find yourself getting 0 when you plug them in, you want to double check and make sure, ooh, did I accidentally plug back into f prime? I don't care what f prime is at these values. I've already used f prime to do any analysis I want for that. I'm going to plug back into f. When I plug in 0, I get 4. When I plug in 1, negative 1 plus 2 plus 4, I get 3. That can't be right. Wait, 4 plus 2, 6, 5. Huh. And then when I plug in 3, negative 9 plus 6 plus 4, I get 1. Okay. So here are my possible values. My max and min are going to be one of these guys, and I just have to pick. What is the absolute smallest number on this list? Right there. The absolute min equals 1. What is the absolute largest number on this list? right there. The absolute max equals 5. That's exactly what I expected because I decided there was a max at 1, but now I've confirmed that is the absolute maximum value. And this guy, he is not an absolute max or min, and he's not a critical point, so I'm going to cross him off. I'm not going to consider him a relative min. If you say a relative min, your teacher will probably not take points off, but he's really not a relative min. And that's it. I'm done with this problem. Woohoo! That's how you do max and min problems. I hope that you found this helpful. Like and subscribe. See you next time.